So now that you have seen the basics of crystallography, so what we will be talking in the next 1 hour and so on are on a new system of charged metal oxides which are colloidal. That means they have length scales which can be from 100 nanometer to a micrometer. And we will be talking about these charged material systems. Now, these are conventionally known as soft matter systems. Soft matter system means, for example, you are sitting on this chair, right, which is soft, right? So, if you think that why some material is soft, then you need to think about the reason, and the intuitive reason comes out to be that they are more squishy, meaning they can just come closer, at times have boundaries that can intermingle and then go away. So, this concept of soft matter was introduced by Professor Pierre Desjardins, who got the Nobel Prize for this ideation of soft matter, where he gave a very nice analogy. So, what did he say? He said that if you look at the Great Wall of China, it was there, is there, will be there. So, when you have a state of matter that has boundaries which are immobile and which are fixed, then that state of matter is proposed to be called as solid state of matter. But then he also said, if you look at the boundaries of Middle Eastern states in Middle Ages, those were diffuse, mobile, they were ever changing. So he said, when you have a state of matter that have these type of boundaries, then those type of matter can be called as soft matter. Now, in around middle of 1990s, there were some systems which were being observed with charged metal oxides. Now, these are known as polyoxometalates. They were discovered. Now, what are those polyoxometalates? As the name suggests, poly means many, oxo meaning they have oxygen, and metal meaning they have metals, and ates, this suffix ates stands for negatively charged systems in classical coordination chemistry. So that means these were molecular clusters comprising of many oxygen, many metal, and a charge. So these were the polyoxometalates. But then people observed that if you take them into dispersion, meaning you have the crystals, you take them into dispersion, then they start scattering light and they have a diffuse boundary and they start behaving in an interesting way. That means they show Tyndall effect. You have studied Tyndall effect, right? So if you shine laser or light, they scatter light. So all these effects started building up or showing up. So instead of reinventing the wheel, what we thought that we can apply the concepts of soft matter and graft it onto these special type of phases of oxometalates. So we proposed that polyoxometalates or oxometalates are the ones which are in the crystalline domain. They are like the solid state of matter, like they are having the boundaries, as Professor Kari Risanen has been showing you. They were having crystalline state, so crystalline boundary, hard state. And then you have this other state which are soft, mobile and diffuse, like the boundaries which Pierre Desjardins or Professor Pierre Desjardins was talking about, where the diffuse mobile boundaries of the Middle Eastern states in Middle Ages. So we propose to call them as soft oxometalates, right? So that means they are like liquid. You can have a charged metal oxide as a liquid in a bottle. Okay, so I'll be talking about these soft oxometalates in the next 45 minutes to 1 hour, and then I would also request you to ask questions wherever you have doubts or confusions. Now, with this I start, and of course, this work is only possible because I have a fantastic lab here at ISER, and we have been doing this work for last 15 years or so. So we have been developing this area slowly in bits and pieces. And this is because we have a fantastic group of dedicated students in the lab. They work very hard and they are very bright and young people like you who create these results. So I am thankful to them
for this, and they are also behind this organization of this GYAN program as well. Now, having said that, let us get started. So, I give you an outline of all the lectures on GYAN, which GIN program, which I will be doing. So, I will first be giving today class 1 on soft oxometalates. Then the class after this, that means that is also today, I'll talk about microbubble lithography and catalysis. I'll show you how you can make patterns and how you can do catalysis with these type of patterns, right? So, which is also quite interesting. And I'll show you that you can make plastic conductors, you can make catalytic chips, all on nanoscale and microscale. And then in the third class, I will talk about soft oxometalates in catalysis. So, I'll show you examples of catalysis and what are the catalysis that you can do with these type of systems. And finally, on the final day, I have for you an innovation and entrepreneurship workshop, because I felt that most of us are not taught in a conventional sense the basics of communication, that how you talk, how you present yourself, and how you can think out of the box, whether you are going to work for industry or whether you are going to work in academia. So, I'll talk about those things in a packed manner, and I'll ask you to do some assignments also on that day, and I think you will have fun. That's the final day, and we will have a workshop where we will ideate, and everything we will tell you, and I hope you will enjoy. So, the basic idea of this course, as me and Professor Kari Risanan has been thinking about, is not only to have the basic but also have a little bit of applied high research, and then ending with a scope for you, for example, to ideate on projects which have applied directions as well. And you can perhaps think of not only academic projects, but also perhaps you can think of innovative projects as well. So, that's the scope of this present GYAN course which we have taught, and in between we will have others also giving you the lectures on different applied aspects of basic crystallography, which you will be learning from Professor Risanan. So, let us get started. This is IISER Kolkata at a glance, and some of these beautiful pictures were taken by my students, so I am showing them. So, it's really beautiful campus, you enjoy the campus, and there is a lot of natural flora and fauna. So, be careful from the natural fauna, because just now when we were coming, we saw some very interesting animal. So, I would request you to have covered shoes and not to go too deep into the forests and things like that, but just walk on the main, and the nature here in the campus is beautiful enough to impress you, even when you are taking walks in the main roads without walking into the woods and inviting any unnecessary awakening from the faunas of this area. So, now this is IISER, and and we are now in this building somewhere. So, this on this side. Anyway, so about our academics, so I just tell you about our lab. So, our lab is an excellent lab, for example. So, we have so far published around 110 publications in good journals like NatCom, Angawante, Coordination Chemistry Review, Journal of Materials Chemistry, and so on and so forth. And we have also few patents, and we have also co-authored few books. So, that is to convince you also that you are hearing from someone or from us who are also working at a very high level in research in this field. Now, let us get started. So, as I said you, for example, if you are interested, you can have a look at this review. So, this is a recent review with Nidhi Kumari in 2024, and this one. So, as I said you, so these soft oxometalates are the soft matter state of charged metal oxides. And why they're important? They're important because they can serve as a possible model to understand crystallization. And I will tell you how we can use this model to understand crystallization. And not only that, it's also possible to explore kinetic states. And once you can explore these kinetic states, so then you can explore the possibility of photoredox catalysis. So, you can do photoredox catalysis because there is a presence of thousands of photoactive metal oxo terminal bonds. So that means when you shine light on them, or if you can excite them with electricity, they go into the excited states. And of course, another thing I would like to point out is that with structure from crystallography, you have the periodicity, you have the periodic boundary. But what happens when you cross the periodic boundary? What happens, for example, like about the structure of these foamy seeds, or the milk that you drink in the morning, or the coffee that you had in the morning? Have you thought of, for example, like why when you leave the coffee, there is a coffee ring at the bottom of the cup? These are all the paradigms that you can understand from the point of view of these transitions of soft matter into crystalline domain. And I will show you with case by case examples that how this type of material addresses the structure beyond the translational paradigm, beyond the translational periodicity paradigm. So this is important system to understand different methods of crystallization, and we will show you different transitions. Now this has also been getting some traction from the practitioners or researchers in the field. And so for example, Professor Mark Antonio, so this is Professor Michael Pope, who is like the Pope of the field of polyoxometalates, and he wrote the Bible of polyoxometalates. And in that work, he highlighted in the Encyclopedia of Inorganic Chemistry, he highlighted, and his student highlighted our concept of SOM. So which was quite nice, and we liked it, of course, with Professor Tatiana Vogt, Mark Antonio, and so on. Now, what we are planning to do, what is it that we are looking at? So what is it that we would like to do or we can do with these type of systems in the next coming 10-15 years? We would like to have a platform type of material where you can do integration as well as differentiation of material, and you can create active matter, meaning that mobile matter, meaning the moving matter. So it's not only that bacteria or viruses can move, we will show you that you can indeed make motion or create motion by using these type of materials which are like life, which are lifelike. Now if you have this kind of lifelike, and if you take a systems chemistry approach in materials design, then what you have essentially in the center of this whole structure, you have the energy, and then what you need to do is you have to partition the system. Once you partition the system, you have immobile frontiers, closed systems. And from your basic thermodynamics, you know that your laws of thermodynamics are applicable for closed systems, right? Because if you have open systems, then thermodynamics becomes complicated and you have different types of thermodynamics. So you have to have a closed system. You have to create partitions, you have to create vessels. And then you have to have reaction within these partitions. Once you do reactions within these type of partitions, then what you do, you essentially come up with harvesting of energy. So you can really take energy out of the systems. That means you can harvest, for example, solar energy or wind energy, and then you can harvest energy and you can use them in daily life. And I will show you with examples how using these type of systems we are able to convert carbon dioxide into fuels like methanol, ethanol, and so on, acetic acid, and so on and so forth. And then you can use reaction also to create motion. You can harvest motion, right? So you can make them move and you can have motion in them. And you can also use assembly and disassembly to create motion. So this is essentially the paradigm. I will give you examples of all these type of cases. The idea is then smart people like you who would later come and enrich us will perhaps be able to one day to integrate these systems to come up with artificial life-like systems, right? So that's basically the idea. So the output will be integrable and differentiable active matter systems. Now I give you first example. For this is what we collaborated with Professor Benthang and Professor Francis Fairport from China and Ghent University, Belgium. So what we did, we combined this type of JUCZ12. It's a porous organic framework. So we use this porous organic framework, and then to it we added the SOMs, the soft oxometalates. What we were able to get, we were able to get this SOM JUCZ12 nanocarpet, right? So that means you get a combination of both these, and that is based on charged interaction, right? So you have a complementary charge, one is positive charged, one is negatively charged, then you get this type of systems. Then what we did as a fuel, we added methanol and acid a little bit so that we were able to reduce these SOMs into more reduced state. Now if you know that you are reducing your system, you immediately then know that you are pumping charge in the system, right? Negative charge you are pumping in the system. This would then reduce the interaction between the porous organic framework and the SOMs, and thereby there will be disassembly, right? So they will be moving away from each other, and that is exactly what happens. So there is a disassembly, and the disassembled oxometalates are released from the micropores, and this as an output gives you autonomously moving nanocarpets. So that's the output. So that means you start with an input, you are able to program it, the programming is your structural units, and then based on the interaction between these structural units, you can create motion. And this is something which we observed in real life. We analyzed the particles, for example, using TrackPy, so that is a Python-based systems. And this work was done by Apabrita Mollik, who is now in Czech Republic doing her postdoc. And what was the motion? You can see, so Apabrita could get this type of particle. This is in 0 second, then in 1 second it moves like this, and then in 9 seconds it moves really along this trajectory over there. So there is nothing except this chemical interaction between the positively charged and the negatively charged particles, and we are charging them up to get this motion. So now one of the ideas which my present colleagues are trying to pursue is, can we do this together with catalysis? And I will show you perhaps in the third class where you can do water cleaning with these type of systems. So they are like, you put them, these particles, in water, in dirty water, which was done by Apabrita also earlier. So you put these particles in the dirty water and you clean up the system totally. So which is quite cool and which is quite of a nice application. So we always believe, for example, in the application of the work together with the high level of fundamental science. And I would also like to urge you to think along those lines. Now this is one system. Then I'll show you, for example, the next system, that is understanding crystallization of oxometalates starting from the SOMs. Now what you see in this case is as following. You have this charged metal oxides, right? Like for example, we started with the most simple MO7 type unit. It's a heptamolybdate. It's MO7 O24 6 minus. It's a very basic unit of molybdenum based oxometalate. Now what we wanted to do the following. It's very difficult to understand crystallization, and it's a challenging problem. So how crystals are formed? So in order to do that, you have two competing processes that are going on, right? So one is the physical process and the other one is the chemical process. Now in the physical process, it's perhaps relatively easier to understand, but if you have both the processes going on, then it becomes very difficult to understand. So we took MO7, we made sure that there is no chemical reactivity, right? So this was a work that was done by Preeti Thomas, who is a graduate student of our lab. So she finished her PhD. So she took these MO7 type systems, and then without any possibility of any chemical reaction, right? And then what she did is she increased the volume fraction, the concentration. Now, once you increase the concentration, once you started increasing the concentration, this clear solution of discrete ions started giving way to the colloidal soft oxometalates. How did we know that? It was known because when we started with the simple solution, when we shine light on them, there was no Tyndall effect. It was a clear solution. So for example, if you take a laser pointer like this, and if you have a container with water, you shine laser, you will not see the path of the laser through water, right? There is nothing, so there is no scattering. So when you take this molecular liquid kind of thing, so this MO7 units only the ions, molecular ions, then you do not see any scattering. But what she found, if she raises the concentration of these ions, then she was able to see scattering. That means they were forming colloidal units, right? So this is what she observed. And then if she raised this concentration further, she was observing crystalline polyoxometalates. So absolutely crystalline domain. So that means she was experiencing the transition experimentally from soft oxometalates, from molecular liquids, molecular ions, to colloidal entities, to the soft oxometalates, to the crystalline polyoxometalates. So then we joined hands with Professor Nirmalo Ghosh, who is a physicist, and we looked at the emerging structure in these type of systems, which you can do with attenuated light. So I'm not getting into that, but you have to believe me that we could see the emergence of crystalline periodicity in this system. And what we then observed is that we were indeed getting a system where there was no periodicity at all, right? The MO7 units. Then there was an emerging periodicity. That means there was some local periodicity which was showing some kind of emergence of order in the system. And then finally, there was a total order in the system because we could get crystals, we could get diffraction patterns, we could get crystals. So this was a transition, and then we explained it also theoretically. And what we did, we took this kind of rods and then we put Baxter type potential. What is this Baxter type potential? Baxter type potential is that you have a rod, then around the rod you take a very thin potential window, very, very thin. It's infinitesimally thin potential window. And when two particles come close, that means within this potential window, they are locked. They come close together, they are locked, and then they form extended units. And like this, there is a domino effect happening when all these particles are coming close and they are like locking with each other, and then thereby they are forming the crystalline polyoxometalate from the soft oxometalate. So this was our explanation, and the beauty was we could calculate from this Baxter model the osmotic potential, meaning you know osmosis, right? So when you have an osmosis, you can have an osmotic potential. So you can calculate that osmotic potential, and we had it similar as the one we could get from the dispersion studies experimentally. So this was a very fine piece of work. Then my other student, for example, a little bit later, Shaunik Pal, who is now in Czech Republic as a Marie Curie fellow, he took up the problem, and we thought that now we give it a little bit of spin, a little bit of twist. So what we do, we change the pH of the system slightly, right? We are not doing chemical reaction, but we change the pH. What is the beauty of changing pH? Because you are changing the hydrogen ion concentration. Now, once you change the hydrogen ion concentration, then what happens is you are setting in a metal oxo metal condensation. That you can understand, right? This is from your bachelor studies, you have perhaps studied it, right? So you have MO, then H, you put another H plus ion, then you have MOH2 plus with the oxygen having the plus charge, right? Then you have the next MO terminal unit, which will then come and it will form a MOM type unit with the expulsion of water molecules. So this is the type of condensation which you can set in, and that's what he did. And then he was able to show that using this type of systems, changing the pH, it's possible to form MO8 type units, and it also follows exactly the same pathway, meaning you have the molecular anions which are going with the change of pH into colloidal units, and then or colloidal SOMs, and then with higher pH it is going to the condensation and getting a crystalline domain. And we were also able to get the crystal structure which is shown here. So we could easily get this type of reactions, right? And then when we plotted this in a ternary phase diagram, what we saw that within this domain, so there are three parameters: water, temperature, and oxometalate concentration. So we saw that within the SOM domain, there is a crystalline domain of POM. So that means you indeed have a situation where you have the liquid like anions, they're there, then they form this colloidal entity which is a little bit more dense, and within this colloidal entity you get again the crystalline polyoxometalates, right? And this shows, for instance, that you can have a change in phase by just increasing the volume fraction or by increasing the pH. Now we thought that, is there an application? And in fact, I am telling you the story a little bit in a reversed way, because we observed this result before all the nice explanations I gave you in the last slide, right? So what was happening there was with Professor Owen Banerjee's lab. What we were doing, we were taking a SOM dispersion and then we were shining laser on them, but not with this normal laser pointer, but with optical tweezers. So we put optical tweezers and then we were able to heat up this SOM type units, and then we could see that there was a heating up of the bubble. And once you have the heating up of the bubble, then you have a convection. Now, why there is a convection? This is because you know that the surface tension is dependent on temperature, right? So you have a change in surface tension. So that means when you are shining laser in the sample chamber, between the top and the bottom, there is a temperature gradient. Now this temperature gradient leads to a surface tension gradient. So when we were having this optical tweezer leaving its spot, we were seeing this convection. This is the same type of convection which you see, for example, if you take a glass of wine and you swirl it, right? And then you will see the tears coming on the glass walls. This type of convection is known as Gibbs-Marangoni type of convection or Gibbs-Marangoni effect. So because of this type of Gibbs-Marangoni effect, there was a convection current, and because of this convection current, the cooler part were having the SOMs and the hotter part were convecting the SOMs onto the base. Now when you are moving away the laser tweezer, you are suddenly cooling that part, right? And that induces a phase transition, and that would lead to the deposition of the crystalline polyoxometalates on the glass slide. And I will show you in the next class a little bit more detail what are the applications you can do and how you can do fine reactions like polymerization and so on and so forth. So then we were able to show it with Raman spectroscopy that indeed you have a transition from the breathing mode of these vibrations, which are on the range or on the sides of these nanotubes, towards the more crystalline domain. And then what we did, we also did a study where we were able to convert benzaldehyde to benzoic acid on these trails. So we not only formed trail, but also we did catalysis with this, right? And benzaldehyde was oxidized into benzoic acid, and this showed a sigmoidal curve. Now the sigmoidal curve, as you will know, represents that there is heterogeneity in the system. This is very typical for heterogeneous catalysis. So we could do site-specific catalysis with light using these SOM type systems. And I will show you in the next lecture what are the other things that we can do. But this showed a very interesting phenomena. What is the interesting phenomena? The interesting phenomena is that they are light active. SOMs are active or responsive to light, right? And then we were happy that Professor Masaaki Haga from Chuo University, he is also a leading figure of inorganic chemistry, cited our work quite in detail. So he said, for example, Roy et al. Have demonstrated continuous depositions and a line patterning of polyoxometalate molecules using the translated bubble. So this also shows the power of collaboration, you see, because this work was possible because of our collaboration with Professor Owen Banerjee. Using the laser physics, we were able to uncover a fascinating aspect of these type of systems, which we are now pursuing in our lab. So one of the systems which we have now got is a ZIF67 type system, which is a MOF, on which Khokon Manna, he is working on this. So where we show you can have water oxidation in these type of systems. So now, having talked about it, having said the photocatalytic activity, what we then used with this was the nice idea that was executed by Shontu Das, who is now a government servant working in a very high position. And so he observed that if you would see the SOMs, and if you would shine light onto the SOMs, then they go into the excited state, right? The SOMs go into the excited state. It is similar like what Professor Karirisanen showed earlier with the electrons being kicked out and they are moving into the excited state and there are creation of holes, right? So what are photons? So for example, when you have the photons, so they impinge your SOM, and then what happens is that the SOMs go into the excited state, but they cannot be in the excited state forever. So that means they have to come down to the ground state. Now when they come down to the ground state, they emit an exciton, right? And you know, exciton is a combination of hole and electrons, right? So you have this hole and electrons combined. So what does the hole do? So the holes, they oxidized water into oxygen, right? And that's what is shown here. So water was split into oxygen by the holes, and then the reducing equivalent, because you know, if you break water, if you write the equation, you will get this type of equation for water oxidation, right? So that is 2H2O. If you write it, the equation, you have O2 plus 4H plus 4 electrons. So you have these protons and electrons together with the electrons. These are the reducing equivalents which were then injected into carbon dioxide, and Shontu was able to do that together with Shubho, who is now working in a company in Germany. So they were able to show this, and we were one of the early ones to convert carbon dioxide into formic acid together with oxidation of water. So this was a coupled process. It's like photosynthesis, so that's why these type of processes are known as artificial photosynthesis, right? So where you do photosynthesis, but then you don't have leaves, you have these SOMs, you have these entities which are then doing the magic for you, right? And at that time when we published, it was one of the highest turnover number systems with almost 1.4 million turnover number. And this is comparable to another system which was reported by around similar time by Professor Omar Yagi and Chris Chang with cobalt porphyrin based systems, and they published it in Science, so which showed a turnover number of around 0.29 million. So that's the level which we could reach. But then we realized that we cannot go, or we cannot push so much with these systems. Why? Because these are OXO systems. Now with the word OXO, you know that they're intrinsically oxidizing, right? So when we wanted to have more reduced systems, we were not successful. We could not get more reducing system or more reduced systems. So then Shaunik Pal, so he's another PhD student of my group. Now he's working in Czech Republic. So when we joined hands with Professor Wolfgang Schöfberger from Austria, so he was able to show that you can change these ligand systems into corol type systems with a cobalt and a triphenyl phosphine. You are able to reduce carbon dioxide into ethanol. And when we did that, it was having also one of the highest turnover numbers, and it was also having one of the highest Faradaic efficiency. So we had, of course, a collection of different reduced products, but ethanol was obtained at a Faradaic efficiency of 47%. So which was really, really high. So what happens here is, for example, you have the carbon dioxide, then you have the reduced system, then you have the carbon dioxide anion, they will combine together to form glyoxal, right? CHO, CHO. And then you have a disproportionation via which you create ethanol, and that's how you can get the reduced product. Now, having said that, it's also possible for these type of systems to get these type of reduced products, and we then thought that what happens if we change this cobalt and we can change this to cobalt into manganese, then what happens? Then we were able to get carbon dioxide a little bit less reduced, but to more oxidized product like acetic acid, right? Because it's more oxidizing, so we could get into acetic acid. And later on, very recently, I will show you then what with these type of systems, we thought of changing the systems, and we went on to a different kind of systems with the sulfur containing systems, MOS2 type systems, and we were able to have this sulfur vacancy, and then with this sulfur vacancy you can create electron containing pockets. Now, instead of working with the oxo, we now move to another chalcogenide, which is the sulfur containing chalcogenide, and then we were able to create the sulfur vacancy, and with this we were able to induce phase conversion of MOS2. Now, this was a work done by Kaushik Dash, who is now in Germany doing his postdoc. So what did we see? So Kaushik showed that you can have this type of sulfur vacancies, which are shown in VS, and you have the two types of phases, so in MOS2, so the 2H phase and the 1T phase, and it was based on the residence time of carbon dioxide into these phases, which would then convert carbon dioxide either into more reduced methanol or into less reduced formic acid. So this is what happens then. I show you. So you have initially you have a system which is mixed with 2H phase and 1T phase. Then you have a phase conversion. This is done by sonication. You have the sulfur removal. So you have the sulfur vacancies. In these vacant sites, because you have high electron densities, so the carbon dioxide comes in and locks there, right? So the carbon dioxide comes and sits there in this manner. And then with blue LED, we are able to convert carbon dioxide in these holes either to formic acid or to methanol. And what you can see that basically the difference between the 1T and the 2H phase, how we can see it from the transmission electron microscopy. But what is important is that initially you have a condition where you get formic acid, but with time this formic acid starts getting converted into methanol and the formic acid concentration goes down. This is under open condition, and under closed condition you have always the formic acid, which is the dominant product. So if you have this, so this means that initially you have the formation of the formic acid, but when you expose them more to carbon dioxide, then they go to more reduced species, and that is how methanol is being formed. and we investigated it also with in situ IR spectroscopy, and we were able to show that how the emergence of the bonds take place, and that is how we came up with the explanation of the mechanistic pathway for these type of reactions, which was going via the methoxy unit and then forming methanol, or it was going via the formyl unit and becoming formic acid. And this was a work also where the theoretical works were done by our colleague in IISER Pune, Professor Prosenjit Ghosh. Now, what is interesting is that you have these type of systems, but we thought that means we are moving from chalcogenide to the pnictide. So we thought we can change it from chalcogenides. We have shown it with oxo, we have shown it with sulfur systems. Can we change it to nitrogen based systems and see what happens? And then it was Nidhi who took this challenge up, and this was a molecule which we got from Professor Shonjit Ganguly from St. Xavier's, and Nidhi took this challenge up, and then she was able to convert carbon dioxide into a series of products including ethanol and acetone. So I'll show you what happens there. For example, you see now when you do electrocatalysis, how do you see or how do you know that you have any reactivity going on? This is a very simple question, right? So when you do electrocatalysis, so the first thing that you can do is you can run a linear sweep voltammetry curve, just a simple LSV curve, right? And then you run it in argon, that means where you have no reactant, and then you run it in carbon dioxide, right, which is your reagent. So if your reagent is nitrogen, you run it with nitrogen. So you run it with carbon dioxide, and then immediately if you see there is a gap or there is a change in the potential, then you immediately know that some of the electrons are getting chewed up or taken up, right? So why is the electron being chewed up, or where are the electrons going? Then it was Nidhi who found out that these electrons are then going to reduce the carbon dioxide, right? So you are generating, essentially you have an electrode plate, you have an electrode, and then from the electrode you are charging the electrons onto your electrocatalyst. This electrocatalyst is then taking up the electrons and getting into a more active form. So you whatever you have, you essentially have a pre-catalyst that is going into the active catalyst, and this active catalyst is nothing but a diradical. That's what she showed, and we could see from the change in the distances. So this was like before electron reduction, it was like 1.26. After 2 electron reduction, it was 1.37. So that means there was an extension in the bond length, right? And then we had a twist in the amine groups, and where we had this carbon dioxide coming in and latching. So there were two types of sites. One was the end-on site and one was the side-on site. So where these type of combinations were happening. Now once these combinations were happening, then we were able to show, or Nidhi was able to show, that they go via acetyl unit, and these acetyl units would combine with methyl so as to form acetone type units together with acetic acid, and the Faradaic efficiency what we got in this case was 30.7%, which is quite positive and quite high in these type of systems, right? And this is the mechanistic pathway where you have the acetic acid pathway, where you see how the carbon dioxide, for example, comes on and sits on these type of azo groups, and then you have the creation of the acetic acid, and then you have expulsion of water together with the formation of the acetic acid in one pathway and acetone in the other pathway. This was a very detailed work which was done by Nidhi, and which shows that we have now come to the C3. right? So one was C1, which we have seen, formic acid. We changed the systems. Then we had C2, right, which was ethanol and acetic acid. Now we are in a position to come to C3, which is now C2 and C3, which is now acetone and acetic acid. So the next step which Nidhi and all others are working on is to get to butane or butanolic system, because you know butane is the cooking gas, right? So it will be fantastic if you can convert carbon dioxide into cooking gas, which will be really, really super cool and quite exciting to look at. So this was a paper which we published with Nidhi and Wolfgang and Shonjib, and if you have time, you can have a look at it. So with this, I think I have been able to show you that what we are trying to do or what we are aiming to do. We have in our mind a type of a quadrangular system or a quadrangle where at the center we work with energy, then we use partition, and then with this partitioning we do reaction, and then here we collaborate also with other labs, and here is the reaction phase where we can harvest energy. And I have shown you C1, C2, C3, and that's where we are, and hopefully we will be able to go to C4 and even higher systems. And then we are able to create motion, and then with assembly and disassembly we are also able to create motion. But the question is, can we develop systems which can do everything in a modular fashion but integrated together hierarchically or structurally, right? So that's the thing which we are interested in going. So what's next? So I have shown you SOMS as a platform for catalysis, lithography, and crystallization. And I'm not taking this introduction into time jail. So what's next is, in the next class, we will do microbubble lithography and we will talk about catalysis. So, and with this, we will go on to the third lesson on soft-oxometalates in catalysis. So this again, I re-emphasize, it's possible because of the bright students with whom we are able to work at IISER. So they work at a very high level, very dedicated, and really I was blessed with a set of excellent students and who are super charged to do things, to do their work, and also at a deeper level. So I would like to conclude with a note which I like very much. One of the scientists whom I have a lot of respect and who is inspiring us, not only me but all of us, is Louis Pasteur, right? So I am very, very much of a follower of Louis Pasteur. And you know, Pasteur was someone who was interested not only in basic sciences but also its application. But he worked at a very high level. And it was Pasteur's interest in wine that would lead to the ideation that germs are in fact responsible for transmission of disease. And he was the key person who in fact ideated this concept, which was later on taken over by Alexander Fleming and the invention of penicillin, and the rest you know is history. Not only that, Pasteur was also another person from the tartar crystals which you get in a wine vat. So when you make wine, you know you have these huge containers which are wine vats, you get the tartar crystals, and in these crystals he found handedness, which today is a huge industry of pharmaceuticals where you have the left-handed and the right-handed products and all this. So what I would like to inspire you is to, of course, do cutting-edge science, but do science with an eye on application. What is the need of your science in your society? And I'll consider this whole effort to be successful because we are combining a top scientist like Professor Kari Risanen, who will be teaching you basic sciences, but of course he's also doing science at a very high level with basic and as well as applied. And we will have also other scientists like us who'd augment it with applications of crystallography, right? And then we will have this workshop where I would provide you with raw materials, and hopefully we will come up with some very cool projects which can have applied direction. So with this I conclude, and I am an editor of this journal, so if you have some things, please do send it over, and thank you very much, and I'll be able to answer your questions when you have. Thank you. Questions? Questions or comments, whatever? Yeah, you can take the mic. Yeah. What would be nice is if you also introduce yourself in one line. That's nice. Where are you from? What is your name?
So myself Shagota Chakraborty. I am from ICS Kolkata. And my question is that we are taking the porous organic materials firstly and adding SOMs on that, and then we are adding the fuels. So what changes does the changes in the structure generally occurs that the SOMs are becoming active. So why
Okay,
are
okay,
it's
very
becoming?
nice. Yeah, thank you. So what we are doing, we are providing electrons into the system, right? So when you are reducing, you're providing electrons to the system. Now when you are providing electrons to the system, the surface of the polyacid, which are SOMs, they become negatively charged. So the glue that is between the POF and the SOM, that gets corroded because that is proton based. So that proton is getting neutralized, right? So because of the electron. So you have an electron diffuse layer that is formed, and that would lead to the chopping off of these two units, so which frees the SOMs from the POF pockets, and then they start moving. That's a very good question. Is clear? Yeah, thank you. Very nice question. Any more question or comments? Okay, if there are no more questions, I think we take a short break for 7 minutes, and then we will go on to the next class. Thank you. So yeah, just take some rest and then we will start again. Thank you.